Welcome back to another lecture. In this lecture, the topic is the derivative and rate of change. So let us consider the graph of a function y equals f of x. It could be any kind of function, cubic function, quadratic parabola, or it could be like an exponential function, whatever function, it doesn't matter. We have some sort of function, some part of it, and we have 2 points on this graph of the function. The points are point P and point Q. These 2 points, which are lying on the graph, obviously they have an x coordinate and they have a y coordinate. I call the x coordinate point P A, so I show it with letter A, and the x coordinate point Q with letter X, for example. Okay, and the y coordinate will be f at A for point P, and f at X, you can say f at X for point Q, because we call the x coordinate point Q X. Okay, mind you, instead of calling these A and X, you can use a different notation. You may say, okay, if the first one is A, and the distance between P and Q, the horizontal distance between P and Q, if it happens to be like h units, then in that case, instead of using 2 letters, 2 variables such as A and X, you can say one is A, the other one is A plus H, for example, because it's like h units to the right of point P. Point Q is horizontally h units to the right of point P. Or you may even use subscripts such as x sub 1 and x sub 2. You can say x coordinate point P is x1, x coordinate point Q is x2. So different notations can be used. Now, the thing is that when we have this line, like when we connect point P to Q, and we end up with this line PQ, this line is called a secant line. A secant line is a line that intersects the curve or a graph at 2 or more points. So it's a secant line, and after all, it's a line. So how can we find the slope of this secant line? That is the question. M sub secant. What is the slope of this secant? In other words, the slope of PQ. To find the slope of PQ, we always use rise over run, like in good old days. So I'm going to say rise over run. I remember in the past, in junior grades, we used to say y2 minus y1 over x sub 2 minus x sub 1. Okay, so that formula is still valid. You may say, instead of y sub 2, which is y coordinate point Q, you can say actually f at x2 minus f at x1 over x2 minus x1. You can say it like that. Or you can even say, for example, f at a plus h, if you use this other notation, minus f at a all over h, because x2 minus x1, distance between x1 and x2 is the same as that increment of h. And sometimes it's even denoted by delta x, to tell you the truth. And you can also say delta y over delta x. So this is delta y, and this is actually delta x. In other words, changing y divided by changing x. And that was the definition of slope of a line, if you recall, from junior grades. So we're not like making things up here. If you use the other notation, we can say this is actually f of x minus f of a, then divided by, instead of x2 minus x1, we're going to say x minus a. Okay? So end of the day, it doesn't matter what notation you're using. All of these notations are popular, but you will end up with rise over run, and you will announce that as the slope of the secant line. And it's just this fraction, this quotient is called the slope of the secant line. Okay? So far, we haven't talked about anything like advanced here. We just talked about the fact that we have a line, it's called secant line. It crosses the graph of a function at 2 points. And obviously it has a slope. The slope is rise over run. That's all we said here. And we came up with like a few different quotients, which in reality, they're all the same. It's just like apparently they're different because we are using different notations here. Okay, so far we haven't said anything complicated here. Now this is where the story starts. Point Q starts moving along the curved path of the graph of the function, and point Q becomes closer and closer and closer to point P. Okay, so point Q starts moving along the curved path towards point P, and as a result, what happens to X? Well, X becomes closer to A, right? What happens to A plus H? A plus H becomes close to A. What happens to H itself? Well, H gets smaller and smaller and smaller, approaching 0. What happens to X sub 2? Well, X sub 2 becomes closer and closer and closer to X sub 1, logically speaking, naturally speaking, because point Q becomes closer and closer and closer and closer to point P. Now, if point Q is like extremely, extremely, extremely close to point P, then in that case, this secant line will seem to us that it intersects the graph at only one single point, which will be point P. So the 2 points P and Q will become very, very, very close to one another, such that we can even consider, 1 point. And this line, which intersects the graph at only 1 point, is called the tangent line. So basically, what happens when Q starts moving towards point P is that the secant line starts rotating, and it becomes very, very, very close to a tangent line, okay? A tangent line that touches the graph at only one single point, and that name, that point P, also has a name. We call it point of tangency. That's the point where the graph and the line meet with one another. That's the point where the line touches the curve at that single point. So point of tangency is what it's called. So now all this story that we talked about earlier all of a sudden starts changing, because we cannot say that we're dealing with a secant. We cannot say that point P and Q are like far from one another, because point Q is like very, very close to point P. So what we say is this. We say, okay, now we're dealing with the tangent line, the green line, and the slope of tangent is the limit of the slope of the secant line, okay, as point Q approaches point P. In informal notation, I wrote it. I'll make it a little bit formal. I say, okay, slope of secant, I'll say slope PQ, okay, slope of PQ, as I can say x2 approaches x1, okay, that's what it is. I can say this is basically the limit of f at x2 minus f at x1 over x2 minus x1 when x2 approaches x1. I can use the other notation for slope of tangent. I can say it is actually the limit of f at a plus h minus f at a over h when h approaches 0. I can say that because when point Q becomes extremely close to point P, that distance between, horizontal distance between the 2 points, that is h or delta x, becomes very, very, very small, approaching 0. I can even say this is limit of f of x minus f of a over x minus a when x approaches, of course, a. So you see that we find the slope of tangent using the concept of limits. And this is why in the former courses we couldn't talk about slope of tangent, because we didn't have this tool in our hands. We didn't know what limit is, but now we are using this idea of limit, and we're saying that the slope of tangent is nothing but the limit of slope of the secant when h approaches 0, or when delta x approaches 0. So this limit, I think we have said it in the past, has a name, has a famous name, and we call it the derivative of the function at the number a. And what is number a? It is the x-coordinate of the point of tangency. Don't forget that. So what we're saying here is that slope of tangent, which is equal to this limit, but we said that this limit is equal to a prime at a number a, so we're saying that slope of tangent is equal to the value of the derivative at number a. Okay, so this much we talked about it. And in terms of rate of change that I mentioned earlier, I think in the past grades you have learned that the slope of secant represents the average rate of change of y with respect to x within the two given points of P and Q. So what we found earlier, the slope of secant was actually AROC, average rate of change. That's what it's called. But this one, this other slope of tangent we found, this is called the instantaneous rate of change, IROC. So instantaneous rate of change represents the slope of tangent. Average rate of change represents the slope of the secant line, all right? When we say rate of change and we, like the question talks about 2 points, you would automatically know that what they mean is actually the average rate of change because 2 points are given. But if the question does give you only 1 point, they talk about rate of change at such and such number, then obviously what they mean is the instantaneous rate of change. Even if they don't mention the words average or instantaneous, you should understand which one of these two rates of changes they mean. Okay, so moral of the story is that we ended up with two formulas which are apparently different, but they're actually the same. The difference is only in notation, okay? That's the only difference. So we have a question here. It says f of x equals 5x squared minus 1. It says find the derivative of the function at x equals -1. In other words, they can say find the slope of tangent line at x equals -1 on the curve, which is the x coordinate of the point of tangency. So that's what we want to find out. We want to find out the slope of the tangent line, basically. All right, so first we need to find the derivative. I don't know if there will be room here or not, but I'll try to write it at the top over there. So I'm going to say we're looking for f1 at -1. So that is limit of f at -1 plus h minus f at -1 all over h when h approaches 0. This formula, we had it somewhere here. Yeah, it's this right here. Okay, so 5x squared minus 1. So it's going to be limit h approaches 0. And the function is 5x squared. So it's going to be 5 -1 plus h, okay, squared minus 1. This is f at h minus 1 minus f at -1. So 5 times -1 squared minus 1. This is f at -1 all over h. Okay, we continue simplifying. So we end up with 5h squared plus 5 minus 10h. You have to do the expansion and the calculations. We don't talk about the basic algebra here. Minus 1 minus, that's going to be, this is 5 minus 1, which is 4. So it's going to be minus 4. End of the day, it's going to be minus 4, right? So minus 4 all over h. Then we try to simplify 5h squared minus 10h. 5 minus 1 minus 4 is 0. We don't bother writing it. And then we factor h out in the top because this limit is in its indeterminate form. We need to find the limit. So it's going to be 5h minus 10 all over h. And then we cancel out the h from the top and bottom. We end up with 5h minus 10 when h approaches 0. And the limit is clearly 10. So the interpretation of f5 at -1 is actually slope of tangent at x equals -1, which is -10. So this is what we find. Now, could we use the other form of the formula I wrote at the bottom to get the same answer? Sure, we could. So you can use either this formula or that formula. It doesn't matter. You get the same answer. And I just talked about the fact that you may see different formulas in the textbook in different places, but actually in reality, they're all the same. It's just a matter of notation. You call this a, you call that x, or you call this a, you call that a plus h. So it's the same thing, same idea. So to prove it to you, I'm going to use this other formula, which apparently is different, and I'm going to get exactly the same answer for you. Okay, watch here. So I'm trying to find f prime at -1. So that will be limit of f of x, which is 5x squared minus 1, minus f at -1. So f at -1, if you plug -1 here, it's going to be 5 minus 1, it's going to be 4. Okay, divided by x minus 1, when x approaches -1. So we get limit of 5x squared plus 5, or actually minus 5, right? 5x squared minus 5 in the numerator, and in the denominator we have x plus 1, x approaches -1. Unfortunately, this is 0 over 0, but we are not scared of finding limits, because we are so powerful in finding limits of any function. We have learned so many different techniques. So to continue, we're going to say let's factor out 5, and then x squared minus 1 will be x minus 1 times x plus 1, and then we have x plus 1 in the denominator, which would cancel with the numerator. So we will have 5 times x minus 1 over just 1, and x approaches -1. Now, if you use direct substitution method, if x approaches -1, x minus 1 approaches -2, the answer will be, once again, -10. So you see that slope of tangent at x equals -1, in other words, f prime at -1, happens to be equal to -10, the same answer we got from before. Therefore, if you use this first form of the derivative of a function at a number, or if you use this second form, it does not matter. You always get the same answer, okay? And nobody on a test will tell you why use this formula and why use that formula. You can use either of them. Whichever you feel like it, you can use that formula. You find this one easier, okay, you always use this one. You find that one, use that one. If I were you, I would learn both, okay? And 50% of times I would use this, 50% of times I would use that, you know? Maybe sometimes this one is easier than the other one, sometimes the other way. But you have to know both. You cannot be in the ocean and then not know how to swim, you know? So you got to know everything. When you're doing calculus, there's no joke. You got to know everything. Okay, so what did we learn? We learned that there's two rates of change, average rate of change and instantaneous rate of change. One is slope of the secant, one represents slope of a tangent line. We learned that there's two formulas for finding the derivative of a function at a number. We learned that both of those formulas represent the same thing, which is the slope of tangent at the point of tangency. And we also learned this formula here, and it says that the slope of the tangent is equal to the value of the derivative of a function at the x coordinate of point of tangency. So that a over there, which is the same a here, is the x coordinate of the point of tangency, in this case point P, whatever the x coordinate is. In the example it was -1, and f prime at that number is equal to the slope of the tangent line at point P. Okay, I hope you did take notes. This was sort of important lecture, and these two formulas, you have to do a lot of practice questions to become familiar with them, and hopefully you will do so. Thank you for your attention.